Yeah, I would say let's wait 1 or 2 minutes more, and then we start.
Sure, 2 minutes, I think.
Yeah.
Okay, it's now live.
So people can watch through YouTube, then they don't have to be in the Zoom.
If they are not in the Zoom, then they cannot interact with you at the end, right?
Yeah, okay, but that's maybe the least of the concerns that we have. But yeah, okay. Yeah.
Shall we start? I think, no?
69.
Okay.
Well, I'll give it another minute or so. Let's see if we get a few more people joining. The academic 5-minute delay, so to speak. Actually, I don't know what it is, the de facto delay. It's 10, 15, I think it was a bit too much, but 5, I think it's within reason.
October 3. Yeah. 74, okay. Okay, Ru, if you keep an eye on the people who want to come in, then that's fine, and we can maybe start.
Okay, I think so. Let's start.
All right.
Okay, so my name is João Cardoso. I'm a professor at the University of Porto and a member of the organization of these talks, a series of talks on quantum computing. So welcome you to this series. And our goal of these talks is to provide a forum of presentations and discussions of state-of-the-art achievements and challenges regarding quantum computing. So the talks will focus on computer science aspects and quantum computing engineering and technologies. We have in mind to cover a wide spectrum of topics regarding quantum computing, from programming models and language to technologies and applications. And the speakers are leading scientists and researchers from academia, research labs, and industry. The series is based on cycles of talks, typically from 4 to 6 talks, and we intend one or two talks per month, and sometimes including also panel discussions. And the target audience is mostly based on students, members of academia, researchers, and members from industry. So it is a pleasure to announce the first cycle of talks, which consists of 6 talks. The first talk today by Koen Bertels from QB and University of Porto. On February 3rd, we will have a talk by Federico Spedalieri from Information Science Institute, University of South California, USA. On February 10, we'll have Frank Lehmann from Universität Stuttgart, Germany. And on February 17, we have Ryan LaRose, University of Michigan, USA. On March 3rd, we will have Benjamin Bixel from ETH Zurich, Switzerland. And the last talk of this cycle will be given by Thomas Gaber from Institute for Informatik, Ludwig Maximilians in Universität on March 10. So it is a pleasure to introduce you this first cycle. And thank you very much also for the speakers to having accepted our invitation to give a talk in this series. Just a note that so we have streaming on YouTube, and most of the talks will be recorded. So thank you very much. I'm going to give the word to Pedro Diniz from INESC ID, and he will introduce the first talk by Koen Bertels. Okay, thank you.
Okay, thank you, João. Well, hello, everybody. As Professor Cardoso mentioned, my name is Pedro Diniz from INESC ID here in Lisbon, and it's my pleasure to introduce the first speaker for this first cycle of talks, Professor Koen Bertels, who is with the QB and the University of Porto. Professor Bertels has been very active in the quantum computing field for the last 9 years, and he's been leading a group which was the first to define a full stack for any quantum computing device, and is currently focusing on the development of quantum accelerators and uses the public domain tools that his team has developed over the years to help organizations and companies to develop quantum solutions for their most challenging problems. So without any further ado, Koen, please take it away.
Okay, thank you very much. Yeah, if there are questions during the talk, you're free to ask them, of course. You can also save them for the end. So I'll be talking about, indeed, quantum accelerators, which I see as the next step in quantum computing, because the focus has been a little bit too much, in my personal view, on the quantum physics aspects. And you may remember maybe in 2018, John Preskill, he published a paper and he was saying, let's stop working on the surface code, let's do the noisy intermediate scale quantum computing. Yeah, and that is actually going back almost like 20 years. So that is important to understand. So my presentation, I will give some basics in quantum, but it's never full-fledged, but I will try to highlight what the different layers are that we need to work on. And that basically opens up a lot of possibilities for maybe 90% of the people that work on quantum computing. They should be looking more, let's say, in a different direction. So anyway, what we have is if we do classical computing, we use classical bits. Yeah, so that's a 0 or a 1. It's an exclusive OR. So it's either a 0 or a 1. And in quantum, well, we may even do the same. We talk about qubits. So a quantum bit is now from this slide on named a qubit. Yeah, and we also can have, let's say, the 0 or the 1 state in combination with each other. And then you might say, okay, what is the difference between the two? Well, the difference is that actually you can combine qubits in a way, in an AND way, such that whenever you apply a quantum operation on a qubit psi, here you see the name psi, has two base states, the 0 and the 1, with two amplitudes, this alpha 0 and alpha 1. And the amplitudes are basically the key element in anything about quantum computing, because the probability at some point with which a particular qubit state will pop up as the solution for your algorithm, yeah, is basically determined by the amplitude. Yeah, what is very important to understand is that and again, I've been listening maybe multiple times really to Professor Vazirani from California, on his online course. And he explains in multiple cases, we don't really know why this parallel implicit execution is being done at the in the quantum mechanical world. And it's still a big unknown, but nevertheless, if I have a qubit psi here consisting of these two, 0 and 1, then whatever quantum gate, I do it on the 0 state and on the 1 state at the same time. And so I will come back to in a minute. So I told you that the amplitude is important to determine now what the result will be of your computation. Again, you have here the psi qubit with two amplitudes, and here you see the big I, which in principle we should not. It's not like you read out visually the memory state, because you have to do all kinds of sophisticated measurements, but let's assume it's a measurement. And you want to look at the super combined qubit 0, 1. And so that means that this alpha here, 0 and alpha 1, they represent in principle the probability. So it's in the qubit world, it's called an amplitude. But once we start measuring it and try to understand what its value is, they become probabilities. And how do you compute the probability? Well, it's the amplitude. The absolute value of the amplitude squared is the probability with which the 0 state is the most likely solution, or the 1 state in this particular case. It's important to understand because everything in quantum is a repetition of the same algorithm multiple times, and each time at the end of the algorithm you need to do a measurement, and then you end up with some kind of histogram. I will show that later. Kind of histogram of the solutions that you're obtaining. So that basically means whatever quantum computing is non-deterministic computing. Oh, yep. Oh. Maybe mute your computer if you want, because otherwise I think it's a question. Unless there is a question, then you have to maybe manifest yourself a little bit. But otherwise, please mute your computer. So quantum computing is a form of non-deterministic computing. So we already know that we do approximate kind of computing. Well, quantum is in a way is a similar thing. Again, I will not go into the details, but how many base states can we have? That basically, well, in the classical computer world, we're used to binary reasoning, in which zeros or one. And so in the quantum world, we do something similar. Please mute your computer, please. So you can have, let's say, the X basis state, the Z basis state, and the Y basis state. And here you see a circle, but it's representing actually kind of a ball. It's called the block sphere. In which you see the 3 dimensions represented. And it's only in the Y dimension that you see that you have an imaginary number. And so that means the amplitudes are always kind of complex numbers, but it's not always that they have an imaginary number. And that really depends on the kind of operations that you want to perform on the qubit states. And this is still like very unknown. We are using now 3 basis states, but it could be any number of basis states. But it's kind of a reduction to homogenize the thinking about all these things. Now, where is the popularity of quantum coming from? And I will give towards the end another kind of graph, which puts things a little bit more in a different perspective. But let's simply assume that we have 2 qubits. So on this scale, we have the number of, and this is the word that I added myself, perfect qubits. I will highlight that later on. So if I have 2 qubits combined, that's 2 to the power 2. So it's always 2 to the power n. I will try to write it down here. So 2 to the power 2 is 4, 2 to the power 3 is 8, 2 to the power 10. And it keeps on growing until you reach that is, I don't even know how many numbers that is. But it goes always like doubling the number of qubits states that you can actually represent and use in a computation. Let's assume that you have, let's say, 300 perfect qubits, right? Very important to realize. Then this is even a number I cannot even pronounce in normal English. yeah, because it's e to the power 90. So this is an incredibly huge thing. So if ever we're confronted with, let's say, big data problems, which we know we have to deal with, yeah, these are incredibly huge big data problems in quantum that we should be capable of doing. Now, what is important is in this gray box, yeah, we double the compute power of any quantum computational device we will build by adding one more qubit, because 2 to the power 1 is 2, 2 to the power 2 is 4, 2 to the power 3 is 8, then 16, 32, 64, and this is how it keeps on growing, yeah, incredibly fast. Yeah, this is important to understand. Now, how does the quantum algorithm, how is it going to be executed? Well, let's assume that we have 3 qubits here. So 2 to the power 3 gives us 8 kind of different states, basis states. And so when we start any algorithm, they're all given the same amplitude. Yeah? These vertical lines, yeah, whether they are positive or negative, yeah, they represent these amplitudes, which is the strength basically of a qubit state, of a qubit state in the whole computation of your algorithm. And you see that when you're executing your algorithm, maybe some of those amplitudes, they become negative, and then they again in the next run they become positive again, but they will maybe basically always grow in size or shrink in size. Yeah. And so after executing any kind of algorithm after n kind of runs, yeah, you will see that maybe one of those qubit states has the largest amplitude. In this particular case, these are amplitudes, yeah, and for which we can always define the probability. Yeah. And so the probability is the absolute value squared. That is basically how you make the negative amplitudes also in a positive probability. Yeah. And then if you do that multiple times, you know, the same algorithm on the same number of qubits, this is very important. It's never a single run that you do. Like in classical computing, you always get the right result. Yeah, if you execute it once, yeah, you don't have to repeat it maybe 10 times or 100 times. Yeah, so you have to run multiple times, and after each run executing the algorithm, you have to do this measurement. And then at the end of let's say 10 or 100 or whatever number of runs that you do of your algorithm, you do the measurements, and that gives you some kind of, here I call it maybe some kind of a normal curve. Yeah, and then you know this free meeting will end in 10 minutes. Okay, I don't think that needs to be done. Okay, so this is how you will end up at this particular basis state, this qubit state. Yeah, has the highest probability, and this is then how that will be represented and discovered after n runs of the algorithm. So it's never a single run and a single measurement. It's multiple runs and multiple measurements. That is very important to perform. Yeah. Okay. So how did I start? I'm not going to go into the entire details, but that was when I was at a different university in the Netherlands. Yeah, and I did manage, played an important role to have Intel land there to finance the quantum research. Yeah, because I'm a computer engineer, so I know how to make a computer. And did I know how to make a quantum computer? Well, I still don't really know. Yeah, but I do have I base myself on whatever I did on FPGA related kind of technology. Anyway, we worked for Intel basically on CMI and superconducting qubits. Yeah, and we developed also in that context our own programming language and a simulator, and also we worked on a microarchitecture. So the same microarchitecture for controlling the CMI and the superconducting qubits. I will come back to those things also here. What is one of the big problems that we still have in quantum computing is that the physics people do not tend to agree on how to make this one perfect qubit. Yeah, because the error rates that we have in the quantum world, yeah, well, in the classical world, let's say CMOS, yeah, so the semiconducting kind of transistors that we're using, yeah, this 10 to the minus 15, 10 to the minus 16, yeah. In quantum computing, we're only at 10 to the minus 2, 10 to the minus 3. So there's an incredibly big difference between those two kinds of technologies. That does not mean that quantum has no future. but that we still have to solve a lot of problems, that the quantum physics people have to solve a lot of problems, and actually a lot of other people that are listening, hopefully, to this talk, will also start working on different kinds of applications. Yeah. So that is I think an important observation that we should not forget, because this has not been solved. Okay, let's be very clear. There is no single quantum technology that has a much better performance than any of the others. Yeah. So and of course it depends a lot on companies that are investing, like Intel, Alibaba in China, yeah, IBM in the US too, yeah, but IBM is most on superconducting, semiconducting, and Alibaba also on superconducting. But these are like hypes, yeah, that evolves, yeah. So that is very, very important to understand. So this is an observation that I make, which is important. Yeah, as I said before, it's dominated by quantum physics, yeah, and it's still dominated a lot by this NISQ philosophy, which was introduced by John Preskill almost like 2 years ago. Yeah, but we have to go. I think personally, we have to go beyond that thing, because we don't really know what really good quantum applications are. Yeah, people. So there are quite some number of people that are working on it, but they look more. They maybe focus too much on either superconducting or semiconducting. Well, semiconducting, that's almost impossible because the number of qubits is very low. Superconducting seems to be growing quite well, but still we have so many technologies competing with each other, and that is what I described there. Yeah, and so that basically means that people that are looking at physical qubits, they have to understand how to take the decoherence into account, because if a qubit is put in a state, it's in nanoseconds it go to the ground state, nanoseconds, yeah, in a superconducting. So this is impossible. Yeah, well, maybe they manage to go to 1 second or something. Yeah, but it's extremely fast that you lose the information. And also the way that you do quantum computations, yeah, these are let's say the block sphere. These are rotations, gate rotations in this block sphere, or if you do 2 qubit gates, yeah, there are always kind of errors, because it's a very difficult, very sophisticated, low-level kind of physics that you're manipulating, and so even a deviation in the electromagnetic kind of pulses that you send can make an error in the quantum computation. Yeah. So this does not mean that there is no future for quantum computing, but we still have to do, yeah, we have to really understand, yeah, that it's more than just qubits that we need, yeah, and actually it's not qubits as such, but we need really good qubits, and that is also very, yeah, the table that I showed earlier, yeah, highlights that, yeah, but we need actually much more, and that is basically the core of what we did in Delft. And that I want to continue working now in Portugal, yeah, and actually at the European and international level. You see here how all our full stack, how it evolved from, let's say, the first pictures that we drew on the whiteboard to, let's say, what you see here now is the latest vision of the full stack, yeah, and I'm happy to say that Portugal is very, very motivated, yeah, because they want to be working on testing of quantum software, which is a challenge in itself. Yeah, so maybe important to realize that at the bottom of the full stack, yeah, and I mentioned that in the beginning. I want to be focusing much more on perfect qubits, not on physical qubits or realistic qubits. But we cannot avoid that, of course. So if at some point the quantum technology improves substantially, we need to make the change, and I will explain how we can make the change. This is a little jump in the past to show that even a company like IBM, yeah, and that is like 2 years ago, they were not interested in full stack, yeah, and 1 year later they already presented a stack which is very similar to the one that we developed in Delft, yeah, which is now this one that you see in a larger scale here, yeah. And IBM, I may mention it again, but IBM is a very prominent, yeah, and very rational player in the field. So what is the goal of what I want to talk about? Yeah, is of course, yeah, how do we go from, well, no, I will not give that story because that would be boring, yeah. But we now have this particular kind of full stack. I just want to highlight one thing, yeah, that is like 1.5 years ago, I submitted my 4th quantum flagship project. Yeah, not for none of these 4 I actually received money. Yeah, but Maybe I'm very bad, but yeah, and maybe that is possible. But I went to Brussels because I'm Belgian by nationality. So I went to Brussels and talked to the EU responsible for the quantum flagship. And he went even further and he said that the quantum physics, if they're honest, they would admit that they're not even capable of reaching the 10 to the minus 2 quality of the qubits. So you see there's a big discrepancy between what the quantum physics world is always pretending, yeah, and companies pretending to that, and what we really are capable of doing, yeah. So so again, I will not go into the details because I will explain the different layers later on, yeah, actually in the next set of slides. But this is basically what we need to work on, yeah. So we need to look at some applications, yeah, and we need to work on testing, yeah, and why not start working also on an operating system. And again, here we have our own simulator, yeah, that we developed in Delft, but it's now partly also in this QB, which is a company that I created, yeah, that we can still use to actually execute any kind of a quantum algorithm. Now, what is the big picture? Yeah, the full stack implementation, and I will go into more into details at some point because I will give also one example. Is basically this is the layer in which we are now working in. Yeah, and we've been working a lot. Basically, yeah, this is basically what we did in Delft for Intel. Yeah, is super semiconducting, but I was also planning to look at other kinds of qubit technologies. But in the end, I said like, no, because I'm only repeating myself, and that's not as a scientist, it's not very interesting. Yeah, I just want to highlight here the fact that IBM, which has a wide community worldwide of people using this Qiskit, which is the software and hardware platform that IBM is putting on the market, yeah, is very good because IBM, the Qiskit kind of compiler is capable of compiling for perfect qubits. And this is very important also, as I will explain a bit later also in the talk. So basically what is already available based on the work that we did for the Intel collaboration, yeah, it was a requirement from Intel that everything we did was put in the public domain, yeah. And so that means that we have indeed the full stack, which is more a concept, yeah. The quantum genomics, I will talk about that later, but we made our compiler also for the programming language. Yeah, the microarchitecture, we had a version, yeah, but now we're actually reworking that particular version. We worked on mapping and routing, yeah, because you have the nearest neighbor constraint for qubits. If you have two qubits on which you need to combine an operator on these two qubits, if they're far apart, yeah, that can never be done. So you really have to move them around such that they're nearest neighbor, they're neighbors to each other, and there you can do a 2-qubit operation. Yeah, and we have our simulator, but I will say something about that later on. Yeah, but of course, as I said, we need much more. Yeah, so these are just indications of things that and I will explain this as I go on in the presentation. So these are the things. Not about machine learning. Yeah, let be very clear, because that is not really my topic. Yeah, but everything else we really understand, or I try to understand with the people that I still have. Yeah, we try to understand what that involves. Yeah. Anyway, so the big picture about quantum application development, yeah, is something that we are doing also, let's say, in genomics, because I will give an example in genomics, yeah, done by a Delft PhD student that I still supervise, yeah, Aritra Sarkar, yeah, and maybe he's listening and maybe he's not listening. I don't know now exactly where he's, because he's in India right now, yeah. Anyway, the goal is that we need to develop an algorithm which consists of things that we don't really know. Yeah, and that's why an oracle always makes a prediction about reality. Yeah, if we don't really know how to make an implementation, well, we call it a quantum oracle. Yeah, and that needs to be translated at some point in a full quantum circuit. Yeah, and that we want to simulate, yeah, in our case on our simulator, such that we get real results on the quantum computations. Yeah. So what kind of applications am I now personally working on? Yeah, and that is of course with Aritra and hopefully 2 or 3 other PhD students soon on genomics. Yeah, we work on, let's say, the basic algorithms that we need in genomics, which is the basis of everything in medicine. Yeah, and so that will only become increasingly important, but for every single human being on Earth, not only for Europeans and rich Americans. Yeah, so, and we also started working here in Portugal on quantum economics and finance. Yeah, and here this is just a starting point. Yeah, so we haven't gone very far yet, but we're doing the analysis. But my question to everybody listening now is, why should we not look at anything else? Because accelerators are being developed worldwide on all kinds of applications. Yeah. So why not design airplanes? Why not do traffic management in large cities? Yeah, where we have like overflow and traffic jams and etc. Yeah, you can use it for encryption and decryption of information, and it's ... because you can make an endless kind of list of things that you can do. So this is a clear thing. If anything you want to take away from today's talk, yeah, is maybe look at quantum applications. And again, a lot of the things that we did for the Intel people is basically a public domain. Yeah, and in QB, we're making it into a good operational version that we can share with universities and research organizations. Yeah, and of course, then for specific kind of customers, we can do extensions and improvements of that. Yeah, so this is important to understand. If we make an application, and if everybody listening today, you would start collaborating with other people, yeah, and you would be developing a quantum applications or quantum algorithm, yeah, that will automatically lead to what we call now a quantum library. Yeah, if these things you can do it inside your university, inside your research group, company, or you can simply share it with the world. Yeah, that means maybe we need new quantum gates, which is something that we already discovered. Yeah, doing quantum genomics. Yeah, that is what we are discovering. That we do many more, let's say, mathematical operations that are needed in quantum genomics, but actually in many other applications. Yeah, we also want to increase the number of qubits. Yeah, again, as we are assuming perfect qubits, we don't need, let's say, 49 physical ones to make one logical, one good, reliable qubit. Every qubit is going to be reliable, because if we want to think about the quantum algorithms, you don't want to be involved in, is this qubit still alive, or how do I make this into a logical one? Yeah, and do all kinds of quantum error corrections that you need to do. Yeah, we did that in the first 4 or 5 years. Yeah, and maybe one of my older PhD students, and I call her now a colleague. Yeah, she may be listening. Yeah, that was her PhD on surface code kind of things. Yeah, so why also not also quantum methods with classical logical structure? Because this is also very important to realize that whenever you're developing an algorithm, you will have to repeat certain operations on multiple qubits multiple times, and I will come back to that also later on. So that means that we are combining classical logic with quantum logic. So that is also what OpenQL, our language, our programming language, is capable of doing. So it offers a while and a for loop, yeah, on a matrix of qubits, so that you can do operations. Yeah, and we're still developing these things. So it's not like we already have the perfect tools. This is not the claim that I want to make. A person that will be organized also or invited here, yeah, is doing quantum software testing. Yeah, and this is one of the papers that they published, and I thought that this figure was interesting enough. I will not go into the details because I already see that they go too much, let's say, in the quantum errors. Yeah, and I think there's a lot of things that we make our lives a bit simple, because even then what we have to do is still extremely complicated. So that is all the red bars, yeah, are things that I don't think we should be looking at now at this stage. Yeah, we developed, as I said, our own compiler. So I'm going down in the layer, right? We started at, let's say, the application level, yeah, the library, and then software testing, yeah, which is important for developing an algorithm. Yeah, you end up with a language. Yeah, so we have a compiler language. Yeah, so I will not go into the details. I will simply highlight here two terms. Yeah, C-quasm and E-quasm, because like any classical computer, you have hardware interacting with hardware. Yeah, which is usually is done through an assembler language. Yeah, a binary level, yeah, or whatever representation you want to use. And we're going to be doing the same thing. So we're starting now. Whatever in quantum genomics we will do, and even in quantum economics and finance, we are here in the top left corner. So we assume, as I said before, perfect qubits in a virtual world. So that means we don't really care whether they're close to each other or far apart from each other. If they need to do a 2-qubit gate operation, in this case, it's possible. If we need to have, let's say, if we want to put a constraint on circuit and the mapping and routing, yeah, that means there should be a routing of qubits. Yeah, that is even possible on our topology. Yeah, that we have in mind about. Yeah, but that will always be different. Let's say if it's an ion trap, or a Majorana, or a semiconducting qubit. Yeah. In any case, where the quantum physics people are is in the bottom right. Yeah, is here, and this is a multidimensional world, because you have all these quantum technologies competing with each other. Yeah, and they always reason in terms of real qubits. So 10 to the minus 2 minus 3. Yeah, remember that, and 10 to the minus 15, like in CMOS. Yeah, so and maybe yeah, maybe we will meet each other in a couple of years in the middle of somewhere. Yeah, that is kind of, yeah, where we go again to logical qubits. Yeah, and they are good enough to allow us to make maybe a surface code kind of qubit. Yeah, that is possible, but that is very difficult to predict right now. Yeah. Whenever we have a quantum algorithm capable, or that needs to be tested, yeah, well, what I'm proposing here today are basically classical computers to actually run a quantum algorithm. There is no specific need, yeah, to have a quantum chip, a quantum device to execute quantum algorithms. Yeah, so you can do that perfectly on any classical computer. However, there's a big however, and that's what I'm going to show here. You need to provide an explicit parallel version of your algorithm to any classical computer on which you want to run your algorithm. So one path is, for instance, this one. Yeah, this is one path, and then this one could be another one. And then you can keep on counting, and this is maybe the last one. So you may have a large number, because there may be dots in between. Yeah, you have a large number of final states that if you want to run it on a classical computer, that is what you need to have. Yeah, in terms of memory and compute power to execute that. So the parallelization is really a big challenge. Yeah, which I have. I named this. I named the professor in Porto that is working with me on that. Yeah, as on classical parallelization algorithms on quantum circuits, on quantum algorithms. So that is still ongoing. We don't have any results yet, but this is the basic idea on which we agree as a starting point. Why is that important? Yeah, well, simply because the number of qubits, yeah, I already mentioned, it's 2 to the power n, yeah, is the number of qubits that we need to have. And here you still have the psi qubit as I explained before, yeah, with 2 amplitudes, and the amplitudes are always these complex numbers. So it's a real state and the imaginary state. The imaginary may disappear, yeah, but there are always kind of 2 real components in any amplitude. Yeah, so that's why you end up here with the base number 4 to the power n. Yeah, and this is again a number which is so big. Yeah, I don't even know how to pronounce that. But this is the kind of memory that you need to represent all of the amplitudes of 50 fully entangled or fully superpositioned kind of qubits. Superposition is a superposition of 2 qubits is 2 to the power 2. So there are 4 situations, and 2 to the power 50. Yeah, is this number of numbers that you need to represent. Yeah, and if they're real numbers, you know how many bytes these are. Yeah, so we're talking here about kind of zettabyte kind of quantum classical supercomputers. Yeah, so that is important to understand. So the parallelization is clearly an important mechanism. Yeah, we don't know how many we need to have, but you have already supercomputers on the world that have maybe 50,000 up to 100,000 processors in parallel. Yeah. Now again, if you're looking, if this is your research, the parallelization, well, move to quantum, because even in the classical computer world, We don't even know how to parallelize the software on, let's say, 50,000 processors. We don't even know how to do that, yeah, because that depends on a huge amount of data that you need, yeah, and whatever. So I will not go into that right now, but that's why even the quantum work has clearly positive implications for the classical computer world, okay? So this is just a way in order to show what the parallelization should be looking at. Yeah, is again how many qubits are we going to look at in our circuit? Yeah, and so the small size is maybe 3 to 10, and then you can go up to, let's say, 50 qubits in the medium size. And if we look at genomics, we kind of made an estimation that we need about 110 qubits for a virus. Remember, we're in the COVID period, right? Yeah, so we need maybe up to 110 fully entangled qubits at some point, yeah, to analyze what the status is of the behavior of that kind of virus. Yeah, any case, these are all things, yeah, that are relevant, data movements, the in-memory computing, and the domain analysis. Yeah, how big is the domain that we need to look at to find, yeah, how to make all these quantum programs in a scalable way. Yeah, like how many qubits do we need actually for that? Yeah. So we go again one level lower, yeah, and that means we can say something about the microarchitecture. Now, I was talking always about the quantum accelerator. That means you have to have a logic, yeah, and then you have to go all the way down, such that you have an assembler version, and the C quasum in the compiler, the common quantum assembler, yeah, that is being sent to the digital microarchitecture of your quantum chip. Yeah, so this blue box, yeah, it basically is classical digital, yeah, and so this is like a cache. We know what a cache is. We know a table in which we store the qubit information. That means the qubit states as well as the amplitudes. Yeah, we have measurements that come from, let's say, our simulator. Yeah, QBSim. I will say something about that later on also. Yeah, but the simulator is basically an external to the quantum microarchitecture, and that is only capable of receiving pure quantum single qubit gates, or 2 qubit gates, or 3 qubit gates. Yeah, let's not make it too simple either. Yeah, 1 or 2 or 3 qubit gates that can be sent to the QBSim, that will do all the operations on the qubit involved. Yeah, and then afterwards we can do a measurement, yeah, of the qubit states in QBSim, yeah, and update whatever is needed in the symbol table in the microarchitecture. Yeah, so we do basically a double storage of qubit information in the yellow box as well as in the blue box. Yeah, but why? Because the evolution of how many qubits we need during the execution of an algorithm is a very variable kind of thing. Yeah? It's not always going higher and higher, because sometimes we don't need variables anymore, or qubits anymore, and so we win again space, yeah, and memory space usage. So that is something that we still have to investigate much more, yeah, with computer scientists, with application developers, yeah. And here you do see, for instance, the routing and the mapping, as I explained before, which is part of the microarchitecture. So whenever we have here a particular kind of topology, let's say every point here is a layout of the qubits. Yeah, let's simply assume here I have 9 qubits. Yeah, in this part. Yeah, so that means that these queues, for instance, they look at this particular kind of qubit, and the second one, yeah, is on this one. So that means there's a connection, there's a cable, yeah, quantum physically a cable for this particular kind of instruction with this physical qubit. Yeah, now in QBSim we don't have physical connections anymore. Yeah, but these are all like digital kind of implementations of the quantum chip. Yeah, but there will always be a clear relationship between a queue, yeah, and a particular set of qubits in QBSim. So that is also how we can still do here in this microarchitecture. We can still do algorithms for routing and mapping the qubits inside the QBSim. That means they will have to be moved so that their proximity is good enough to have a 2 qubit gate operation. Again, you can abstract away from that. Yeah, this is not an imposed thing. Yeah, if you don't have anybody or no money to work on it, then you don't look at the routing and the mapping. But if you do, then of course you should never close your mind on routing and mapping for qubits, yeah, because that is maybe another 20, 30, 40 years away before the physics people will have solved that. So in the meantime, we still have to do the routing and the mapping to do the 2 or 3 qubit gate operations on qubits. Okay, so that is important to understand. There's an overall clock, of course, yeah, because in our past when we worked for Intel, yeah, it's basically very clear that there's kind of here we have a bit of flexible time span, yeah, but the closer we go, let's say, to the execution, so once it becomes here in the chip back then, yeah, then the time becomes extremely deterministic, because if superconducting says this CNOT gate takes, let's say, 20 nanoseconds, yeah, then it should be 20. It cannot be 19, cannot be 21. It should be 20. So the timing becomes much more strict and stringent, yeah, the closer we are to, let's say, the QB-SIM. Again, this is a thing you can impose on QB-SIM or not impose on QB-SIM. So in that sense, it's kind of a flexible kind of tool. So let's talk about QB-SIM, which again, maybe there are people from India listening. Well, this was done by another Indian student I had in Delft, yeah, and he made an optimized version of our QX simulator that we had, and now we call it QB-SIM, yeah, because of course the company is called QB-SIM. So yeah, again, we can have a version publicly available, yeah, but that basically means this is a device, a piece of software that runs on a supercomputer, yeah, which needs a lot of memory. But Ravi was very smart in actually reducing the memory usage of QB-SIM, yeah, and we can still run a lot of things on multiple processors for parallel execution. Remember that we need to parallelize the quantum circuit, and if we have, let's say, 2 to the power n50, yeah, it's a huge number of paths that we need to execute in parallel, yeah. So in that sense, we need a lot of processors to do all these parallel executions, yeah, and so that means we need to look at this parallel software, yeah. And then again, if at some point, yeah, we have a good quantum chip, and for me, this is still kind of, yeah, I'm already 8-9 years now in the field. I haven't seen anything working extremely well, yeah. So, but if one company really makes the difference, can be a Chinese company or an American company. We don't have European companies working on it right now, yeah. But if we have a good quantum chip, then we can always go, let's say, do the C quantum to E quantum kind of cross compilation, yeah, such that we say, okay, we're going to try this particular kind of quantum technology, yeah, for executing the quantum algorithm, yeah. So that's why this particular picture comes back into play, yeah. Now I will go pretty fast, yeah. Let's see, yeah, because you have like 5-6 minutes more. Yeah, I will talk now about quantum genomics. Yeah, the basics is basically that, and I'm talking now about pretty old kind of thing, because I created a company called Blue Bee, yeah, not QB but Blue Bee, which was bought by one big DNA company in the United States called Illumina. Yeah, but that was based on what we did there was basically trying to see where this particular short read can be mapped on the reference genome. So this is one specific, very small version of, let's say, the genomics, yeah, human or whatever kind of device or living organism we're looking at. But here it's basically the low Hamming distance here. So it's the difference between the different cell elements. So it's only one that says, okay, if you put this particular short read, yeah, on position 21, then you only have a Hamming distance of 1. Yeah, so that is a very good way in which the sequencing can be done. Yeah, so let's yeah, there are a lot of things that I'm not going to explain right now. Yeah, but let's look at the example that again my Aritra Sarkar did, because that was based on his, I think it was even his master thesis. Yeah, he already did that kind of work. So here you have a reference genome, a very small one for the example, yeah, and an even smaller short read, so just the 2 elements. And then you need to know where does this particular short read maps into the reference genome, yeah. And of course, you can immediately see it's 0 and 1. So it is indeed on this one. So that is kind of what we immediately intuitively see. But what is the algorithm behind? Well, I will give you just in a couple of minutes, or in 1 minute, maybe the different steps. Yeah. Well, you start actually to split the reference genome in segments of short reads. Yeah. And the size of the short read is very important because that has been evolving. Yeah. I think we're now at 150 length of a short read. Yeah. And here I'm just showing you 2. Yeah. But again, this is just an example. Yeah. So that means you store these 3 elements, yeah, these 3 decompositions into a database, a classical database, and they get a particular index. But you see, okay, you have actually 4 possibilities here, and there is indeed the 0, 0 is seems to be missing, yeah. But that will come back in a second. Now you see here the dotted line that I draw here. That shows now we enter the quantum logic, yeah. So that we start imposing, yeah, certain behavior on these qubits, yeah. Well, actually, these are not qubits, on the DNA, yeah, like superposition, to put them in superposition. So it's that now rather than 3 combinations, you see here number 4 popping up, yeah. So that is what you see here in this database. So now I have a full database of the reference genomics, yeah, in our case 4. Yeah, and I need to find now where this 0, 1, where does that match in the full database of the genomics part? Yeah, and now you see here a color difference, and the color difference usually means in science there's something else happening. Yeah, because we are not really here showing, let's say, the genomics part here, but we're showing here the Hamming distance, how good this particular 0, 1 fits on any of the 4 elements of the database. So if I have 2 yellow parts, that means it's a perfect fit. If I have 1 gray and 1 yellow, yeah, or one yellow and 1 gray, we have a partial fit. And if all is yellow, we have no fit at all. Yeah, so that is basically what we try to do in computing this Hamming distance, yeah, of how well a particular short read fits on the reference genome or the reference database. So that basically says, well, that we have a perfect fit for the 0, 0 part, for this one, on the 0, 0, 1 situation in the database. That is basically what this figure now shows. So this is where this particular short read can be fit into the genomics kind of database. Yeah, that is the core idea. So the different steps are shown here. Yeah, I will not explain these things because that would lead too much, because I will simply go through, yeah, these things where the Hamming distances are computed. Yeah, and so I'm simply highlighting here the fact, which I also mentioned in the beginning. Yeah, new algorithm development also maybe mean that you come up with new gates, yeah, or maybe not. That depends on what is available. So this is, for instance, a quantum circuit, yeah, for the step 2. Yeah, where we're using, let's say, a new gate here, yeah, but which does not exist yet. Yeah, so there's a translation step, yeah, from, you see the 2 Hadamars here, they're here too, yeah, but then you start translating this into this particular sequence of steps. Yeah, these are the universal gates that we currently have, and this is a universal gate that we would like to have, or we may never have, but the translation will always have to be here. So you see here that these 3 things are explained in this particular way. And here again, we see here, this is the same X gate, so the NOT gate. Yeah, so everything. So this is a translation in those gate sets here. I will not go into the details because that would simply lead us too far. Yeah, but this is the way in which, for instance, also these qubit gates, yeah, are translated into these universal gates that we currently have also in our QB sim. Yeah, so that is important to understand. And again, you see here that the amplitudes are all 0.5, because remember, in the initial state of your quantum algorithm, they always have all the same kind of amplitudes. Now, at the end of the algorithm, yeah, where the red line is here, yeah, you will have the amplitudes. Some of them are negative, and one is much bigger but positive, but can be the opposite too, right? Yeah, and then if we compute the probability, which is again the absolute value of the amplitude, yeah, and then squared, yeah. So if you do that for all of the amplitudes, these become positive. Yeah. So these yellow negative ones, they become positive. Yeah. And this one stays positive because it was positive. But anyway, it becomes positive, but even bigger positive. So this is the final result. Yeah. For this one run of your algorithm of genomics. Yeah. We will start working, but that depends on QB, for instance. Yeah, we will start working on a genomics microarchitecture. Yeah, you see here there's a DNA database. Yeah, and then I will have to stop. Yeah, because otherwise it would lead too far. Yeah, I will not talk about this because I think that's kind of easy. Yeah, now I'm basically concluding. Yeah, so this is where everybody in the world is working on quantum computing is basically here. Yeah, and I think we should be also moving here. That is what I already said earlier in the talk. Yeah, and then before I give the final slide, yeah, and the most of the conclusions you already know. Yeah, this is the hype cycle curve from Gartner. Gartner is a very well-known IT consulting company in the United States, and they've been looking at a lot of new technologies. And they saw that in the beginning, everybody's super enthusiastic in putting a lot of money into it, including quantum. And then they will reach some kind of top where there's no clear commercial kind of value anymore. A lot of people, companies, organizations, they step out of it. And I think it's for universities and research organizations to not go to that particular hype curve, but to simply say, okay, this is the goal we want to achieve in the long term, and then have a research plan themselves. Yeah, so that I think is important also as a notion, yeah, to understand what that is. So I can be very fast on the final conclusion. Yeah, the goal should be much more on quantum accelerators. Yeah, the 80-20 rule, 80% of the time is done on 20% of the code. That may hold also true for quantum. Yeah, so we need to look at multiple layers, yeah, up to the simulator. Yeah, I think it's extremely important that we start having international collaboration on these things. Yeah, be it, yeah, I had students from let's say from India, China, all over Europe in Delft. Yeah, and now I will have hopefully the same once I stay in Portugal. Yeah, inside QB, I have a lady from Iran, Jasmine Samadi, who will be joining me hopefully in a couple of weeks. Yeah, she will be working on microarchitecture. So international collaboration is extremely valuable. Yeah, and we can still use quantum classical computers too. So that is basically the entire story that I wanted to bring. Thank you very much for your attention.
Okay, well, thank you very much, Professor Bertels. We have a couple of questions here from the chat. There's been also some reactions to those questions, but I'll try to at least frame them in a way that it can be productive for everybody. So the first question that came in was about Grover's algorithm. And the specific question is, can it be made deterministic? And there was also an answer about that in fact there's no stochastic part in it. So if the oracle is decomposed, it is deterministic. I don't know if what's your comment on this, on the deterministic aspect of Grover's algorithm?
Yeah, Grover is indeed used in many encryption and decryption kind of algorithms. Yeah, that is true. But any quantum algorithm, whenever you start combining a large number of qubits, yeah, in superposition or fully entangled, there's a difference that would lead us too far. You always have a wide number of parallel executions of the same algorithm on the same number of qubits. Yeah, and it's kind of a random. It's not a random walk, but the measurements that you do on the result, yeah, it's never that one run will always give you the same kind of result. Because you will always have, let's say 2 qubits, and sometimes you take this qubit, but the other run, you take the other qubits, yeah? And so that is how it's difficult to predict in advance that one result will always give you the same, one run will always give you the same result. So in that sense, the non-deterministic kind of nature of quantum still holds.
Okay. All right. I have another question that is more specific to the work in the QBSIM simulator, which is QBSIM a universal simulator? And also another question is, how many qubits and non-Clifford gates can it simulate? I mean, is this something that you have a handle on this?
Well, that depends. Again, I made that. I maybe was not clear enough, but I will show this slide again. Yeah, that depends on how much memory we have on the computer. Yeah, because the QB sim, yeah, is actually made for relatively. Actually, doesn't mind to have, let's say, 200 qubits, but if they're fully entangled, yeah, or put in superposition, you need these amounts of memory. This is only for 50 qubits. You already see that this is zettabytes kind of memory that you need for memory. So so it's not QB sim which has a limit. It's a classical computer which has a limitation in memory.
So I had another question about your microarchitecture. It has this clock, it has this organization that suggests there's the sequential execution. Are you basically saying that one could decompose, let's say, a larger quantum problem into a sequence of subproblems and in a way compose them, maybe not sequential, but exploring parallel or exploring concurrent composition of the solutions to arrive at a solution to the bigger problem? I don't know if this is. I mean, I look at this picture and it seems a lot of that you've done a sequential composition of subproblems.
Well, again, this is a schema that we used for, let's say, years ago for, let's say, the up to 15 superconducting qubits, physical qubits. Yeah, but now I want to look at perfect qubits and at a higher scale. So I need to be capable of storing intermediate results or final result, but mostly it's intermediate result, because you will see that the number of qubits that you need will grow during the execution, then it will shrink again and grow again, shrink again. So that's kind of variable. So you need to be able to store the intermediate results. You can keep them into the QB sim. That is true. You can keep them. Wait, where's my mouse? I'm looking for my mouse. Yeah, you can store it in QB sim. Yeah. But of course, at some point, you need to release the QB sim, because that depends on how big your machine is, yeah. And you want to store maybe partial intermediate results into the microarchitecture in your own main memory, and then put them back into qubit. Because that is still like a bit unknown. That is still, so it's a good question, but I cannot really give a specific answer to that.
Okay. All right. I mean, I'm wondering if there's any other questions. We had another question going on here in the chat, but there's been a few answers and also some discussion about Q logic operators and how different they are from classical logic operators. And there was an answer about their reversibility. So I think I'll table that question for now. And I'm wondering if there's any other questions going on.
Because I didn't mention that, but that is indeed a very big difference between classical computing and quantum. Is the reversibility. You can always go from left to right classically, but from right to left is impossible. Yeah. In quantum, yes, there is. You can, so that the time is actually bidirectional. It goes forward and backward. So it is nevertheless an important problem. But again, it's a multidimensional world. Yeah. The mathematics behind is completely different. And so it's very difficult to visualize that, but you simply need to represent a lot of amplitudes to represent the qubit states with which you're working right now.
Okay. So I would wrap it up by now. Well, thank you again, Professor Bertels, for your presentation and your time. And so thank you very much. I would like to take also this opportunity to introduce next week's presentation by Federico Sepeldiere from the University of Southern California, who is also going to be making or offering an overview of quantum computing and quantum annealing. So he's going to talk about a couple of example applications on how he has mapped successfully this to, in particular, the D-wave supercomputing. So that's going to be next week. So I don't know if there's any other issues, questions people want to bring up at this point. If not, let's wrap it up. Thank you once again, Koen, for this presentation, and I hope to see you all next week.
Thank you very much. Thank you.
Okay, thanks.
Thank you. If people still have questions, you can still mail me to
I have a couple of questions there, Koen.
yeah, just
Okay.
Google. The QB email is the easiest for me to read. So koenbertels@qb.eu is the one I read. So if you have questions, just send me an email, and then I will try to reply to it.
We are still streaming on YouTube. So.
Oh, okay.
Okay,
Right.
so so
Okay, I'm gonna leave the meeting. Okay, thank you.